Right, so as I understood that almost everybody except maybe one or two persons will continue on to quantum field theory 2 with me, and since there at the beginning I'll repeat the lectures about regularization anyway, so I thought to talk instead about the helicity spinor formalism. So today we'll be talking about the general formalism, and next and last lecture we will consider the most important applications for the so-called Park-Taylor formalism and BCF for Park-Taylor amplitude and BCFW construction. Yeah, just a reminder that next week on Wednesday we have the final exam, and the material is from the whole course, not just the third part. But I'll actually not consider these last two lectures as part of the class, since they're anyway somewhat off the main topic. All right. So what is this formalism, and why is it important? Well, first of all, the formalism that we described so far in terms of Feynman diagrams, which really means taking perturbation theory in quantum field theory amplitudes and doing explicitly the sums over the terms, is algorithmic. It can be put on a computer, so from that point of view it's good. But it has the disadvantage of being exponential in the number of loops and also in the number of legs. So, I mean, it means that the number of Feynman diagrams is about the order of n factorial, I mean, of the order. So that's exponential in n. So that means that no matter the computer capacity, I mean, much less human capacity, but even computer capacity, beyond a few n, it becomes impossible to work with. So I don't actually remember what's the maximum nowadays, but if memory serves, in terms of a full QCD calculation, I think 5 loops was the maximum, and maybe something like 7 or 8 points, something like this. So this is just to give you an idea. So remember, this is using computers, and moreover, so I remember when somebody did I think it was 5 loops in QCD. I remember the talk. I mean, he just wrote a very efficient computer program to do things. But even with the most efficient thing that took him years to figure out, still you cannot go beyond that. So it's while being algorithmic, it sometimes becomes really, at some point, it becomes really pointless to try to use. So people were trying to find different ways to calculate these things. And so one of the things that started developing very early on, but people didn't really know what to do with it until about 20 years ago, was this formalism of so-called helicity spinors. And just to understand what is the difference, we'll get to the formalism itself, but what is the difference? The difference is that in this formalism, well, first of all, we want to find the sum of Feynman diagrams by itself, so without needing to calculate individual terms, but rather to calculate the full sum at once. But how would this be possible? So it's clearly not possible if you think of calculating the full amplitude as it is in quantum field theory. But the thing that makes it possible is to specialize to specific helicities. So In the case of amplitudes, we've seen that they are parameterized by external states, by the description of the discrete external states in terms of both the momenta and helicity, which roughly speaking means the projection of the spin onto the direction of the momentum. So, one tries to calculate things for specific helicities, and it turns out that the one amplitude that is easiest to calculate is the one that is called maximally helicity violating. Now, violating is a little bit depending on convention, so that the non-net measure makes sense in a specific convention for helicity, because if you reverse the momentum, external momentum, you also reverse the helicity. So what helicity violation means depends whether you allow for outgoing helicity to be the same or opposite as the initial ones. But it turns out that there's a convention in which the maximally helicity violating amplitude, or MHV amplitude, is easiest to calculate, and then has a very simple formula. And then people have started to consider a kind of perturbation around this, meaning you change one of the helicities, so this corresponds to a set of helicities, and then you change one of them, and you get to NMHV, where N stands for next to maximally. So, and then perhaps NMHV and so on. Depending on how many points the amplitude is, you can put several N's in here by changing corresponding number of helicities. So that's so let's say a point would be concentrate on helicity, on given helicity. Then you take this as a starting point, maximum helicity violating, and then move away from it. And then finally, there's this BCFW construction, which is a kind of gluing procedure that allows you to construct larger point amplitudes out of smaller point ones. Larger point amplitudes out of smaller point ones. Now, the formalism as it is, it's been developed completely only for 3 amplitudes. And people have been looking for ways to extend this to loop amplitudes, and one can say a few things about that, but not too much. But in any case, this quantum field theory 1 deals with 3 amplitudes, so that's what we'll do. And finally, the last point is that so they're mostly for 3. And finally, they're also mostly, meaning the easiest, the best understood case is for massless amplitudes, massless external states. There's some progress for the massive case as well, but not full description. All right. So let's say the helicity spinor formalism for spin a half. So we will start with spin a half, even though, because it's easiest, and that's how also historically we started. But it's worth noting that the largest impact has been for spin 1 and spin 2, that is for gauge theories and for gravity. That's where it's most interesting. In particular also because, well, those things are what interested experimentally. So, like in the case of colliders, so LHC experiments, for instance, if memory serves, they're looking for something like 8-point amplitudes. They are actually needed. The 8-point amplitudes at 3 level are not known. And then people can use this formalism to calculate them. All right. I mean, they're not known using Feynman diagrams. So this formalism helped. All right. So what is the starting point? Well, so we want to, the name of the problem says we want to use some sort of spinners that have something to do with helicity. And okay, for spin 1/2 you have spinners anyway, but the point is actually that the spinners are not for the state, but rather for the description, for the parameters of the state. Meaning, I want to describe in particular the momentum in terms of spinners, right? So how we do this? Well, so if I have a momentum p mu, the first thing to do would be to take this and to give it spinner indices. And that would be easy because I can multiply with gamma mu. So p mu gamma mu now has 2 spinner indices. But then further, we remember that these Dirac spinners decompose into Weil spinners. And so let's say alpha decomposes into what are known as dotted and undotted indices, A dot. So these are Weil spinners. So this refers to 1 plus minus gamma 5 over 2 times psi. Right? These 2 components refer to the Weil components. All right. So I said we want to multiply these 2 and then decompose this way. So let's write this p slash, that is p mu gamma mu alpha beta. And now I write the Weil representation for the gamma HCs. That's off that diagonal, on the smaller diagonal. And we get p mu sigma mu, well, let's say like this. And this, AB dot. And this one would be p mu sigma bar mu A dot B. Right? So then this p slash is decomposes as we'll call this PAB dot and this PA dot B. All right. But on the other hand, these are sigma matrices. I mean, sigma mu, remember, is 1 and sigma I. So then PAB dot is equal to wait a moment. Oh, yes, sorry. Yeah. No, that's fine. So, okay, so sigma mu is equal to this, but then P mu is equal to P mu, P mu with G mu nu, that is equal to minus P0 Pi. So then PAV dot is P0 minus P0 times the identity, so minus P0, then plus P1 sigma 1 plus P2 sigma 2, then plus P3 sigma 3. Right? So this is PAB dot. And so let's take the determinant of this thing. The determinant then, so on this is this times this, which is P0 squared minus P3 squared, minus this times this, which is P1 squared plus P2 squared, the minus. So then you see that this is equal to minus P mu, which is m squared. So determinant of PAB dot is m squared. Alright? And here comes the important observation. As I said, we wanted mostly the formulas for massless external states. So if this is equal to 0, if the mass is equal to 0, then the determinant is 0, which means the matrix PAB dot as a matrix is degenerate, and in particular that means that it can be factorized, because so I can write, well, let's say m equals 0, results determinant PAB dot equals 0, implies I can write PAB dot as lambda a lambda tilde b dot, because for something like this, when the columns are proportional to each other, then the determinant is 0, as you know. All right. So we're interested, as I said, in massless external state, but external state also means that they satisfy the Dirac equation in this case. So they satisfy, in this, for massless, just P slash psi equal to 0. And further, as we said, we want states of given helicity. And the helicity is the projection of the spin onto the direction of the momentum. All right? So I want given H states. So as an operator, so then the spin SI, if you remember, is the diagonal SU2 in the decomposition of the Lorentz group. Decompose it as an SU2 cross SU2. And then we consider a diagonal part of this, so the average of the two generators. So here, well, how did we call them? I don't know, like M, I think, and N, right? And then so SI would be the operator JI, that is the average of these things. I think with an I probably, I think it was something like this. and then this one satisfied the this one was then in terms of the SO31 was just the natural definition in terms of the spatial components related to rotation. So the Lorentz part of the Lorentz group where J mu nu, where mu and nu are spatial components. Therefore, this would correspond to the SO3. And we have seen that we could represent also this this element in terms of the Lorentz algebra. So the Lorentz algebra would be satisfied if we wrote I over 2 times the commutator of gamma matrices. So that is to say I times gamma jk. Substituting here, then this would satisfy the Lorentz algebra.
When you say diagonal, is it block diagonal?
I'm sorry?
Diagonal means block diagonal. You say diagonal.
No, diagonal, I mean when I have a sum, a product of 2 generators, the diagonal part, I mean this, the sum. I mean the average. You know, so this would be, this means that jk as a matrix, well, j mu nu in some representation can be written as mi ni. That's the statement that this is a direct product group. And the diagonal part means I put here ji, ji. All right, so this is I over 4 epsilon ijk gamma j gamma k. Now, in the case of massless spinors, so when n equal to 0, the helicity basis turns out to be the same as the chiral basis. So the chiral basis, remember, means the ones of the states of given eigenvalue of 1 plus minus gamma 5 over 2. Right, so what we call left and right spinors. So the equation of motion for the massless spinors is this, both for both US, both P slash US equal to 0 and P slash VS equal to 0. Because the difference between the states U and V was only for the master, right? It was plus or minus IN, depending on whether I talk about U and V. But both U and V satisfy, in the massless case, the same equation, P slash equals 0. And we've seen that there were 2 independent solutions of the Dirac equations with an S that is equal to, let's say, 1 and 2. And then we want to see that these things correspond to the chiral basis. So P slash equals 0, but P slash we have written in this way. So this is P dot sigma bar 0 dot sigma bar 0 US of P equal to 0. And then considering, since we want to relate to helicity, we want to define the direction of the momentum. So let's consider that momentum is in the third direction. So that means P mu is E times 1001. Since it's massless, it means that the energy and the momentum absolute value must be equal to E. And as I said, I want it to be aligned in the third direction. So then the equation of motion becomes E, common E. Then P dot sigma also will get, well, no, maybe let's write specifically. So P dot sigma is then equal to it's P mu sigma mu, and lowering the index means I get a minus P in the first term, and sigma 0 is 1. But then plus P times P. Plus E times sigma 3. Right? So this is E minus 1 plus sigma 3. And sigma 3 is 1 minus 1, 0, 0. So this is equal to then 0, 0, 0 minus 2. Right? So let's take this minus 2 factor also common. And then this would be 0. And here I get 0, 0, 0, 1. Now P dot sigma bar is P mu sigma bar mu. So that's minus E times 1, but then minus, so I get minus sigma I in the second term, so minus E dot sigma 3. So this is equal to this being again 1, 0, 0, minus 1. Minus 1, minus 1. This gives minus 2 here, 0, 0, 0. Okay, so taking out the minus 2e, I get here 1, 0, 0, 1, 0. And so the equation of motion is this times u equal to 0. And then, so this s being 1 or 2, or equivalently plus and minus. Then the solutions for this, we actually saw this before, but we'll write it again, would be, this would be 1, and the other one would be 0, 0, 1, 0. So let's check this. So right. So the first line is all zeros. So multiplying anything gives 0. The second line has a 1 in the last position, but here I have 0, so that's also 0. The third line has a 1 in the first position, so multiplies this one, but this is 0. And
it should be 0.
oh, 0, thank you. Yeah. Yeah, and this one is 0 and multiplies 0. All right. Okay. And then this one, the same thing. This is 0, this is 0. And this multiplies the last one, which is 0. And this multiplies the first one, which is 0. So these two are independent solutions. Okay? Good. But on the other hand, we could also check that these have opposite chirality. So, so these are two independent solutions, but they have opposite chirality. Because, well, 1 plus minus gamma 5 over 2. So gamma 5 is taken to be 1 minus 1, 0, 0. Right? So 1 plus minus gamma 5 over 2 is 1, 0, 0, 1, one projector, and the other projector is 0, 0, 0, 1. Right? So, the two chirality spinors are one where is non-zero in the upper part for this, and for this it's where it's non-zero in the lower half. Okay, so this is eigenvalue of, let's call him left. I always get confused what's left and right, but that's a combination anyway. And then this is in the lower part, so this would be right chiral. Alright, so these two independent solutions have different chiralities, but then they also have different helicities. So as I said, the helicity is the projector of the spin onto the momentum. But the momentum was chosen to be in the third direction, so this is just S3. And S3 is 1/2 sigma 3. So it's 1/2 sigma 3 in both, since we, as we said, this is the diagonal, the matrix that acts diagonally in both. Which then means that H acting on U plus minus of P, which by definition is the helicity times U plus minus of P. And now sigma 3 is 1 minus 1. Right? So when acting on this one, this is a lower index in the upper half, so it gives the minus 1. Gives this. Right? So this, yeah, I guess then this is opposite. No, sorry. Yeah. Okay, this is an unfortunate name. I should have called them oppositely. All right. Oh no, no, sorry. There's an extra minus sign. Where was that? There was a minus in front of this. No. Why was the minus there?
When you define the list operator, there's a minus with the notes, but there isn't a minus. I don't know.
Yeah, I'm trying to remember why there's the minus sign here.
S3, this form of S3 comes from what you wrote there?
Yeah. Yeah, I think.
In terms of communication.
Yeah, there's probably. Nah, it's just bizarre, but probably there's a minus sign in here. I don't remember why that is, but it's probably true. I would need to look at the Lorentz algebra again, but it's probably true. Bizarre, because I would have thought naturally you would get in sigma 3 over 2 in both, but well, there's an overall minus for some reason. So if there's an overall minus, then minus with minus gives plus. So plus with U plus, and then the other one, U minus, is in the upper lower. So this one touches this one, which is a plus, but with this gives a minus. So we get plus or minus, U plus minus. And we have defined this for P in the third direction, but one can actually check that this is true for general P. which means that really u plus of p has helicity plus and u minus of p has helicity minus. So left-handedness is associated with chirality, and right-handedness with anti-chirality. Okay, so I guess I don't need this anymore. Where is this? So then this u plus of p will be something with indices. Remember, we split into alpha into a and a dot, corresponding to upper and lower ones. So u plus will be called, well, we'll have two notations for it. One as a ket with lambda plus, emphasizing the plus helicity, but the other one would be lambda a, and here a would emphasize the chirality. And then correspondingly u minus p would be, now we will use a different kind of bracket for this. This is a useful notation because it will help distinguish, if you don't put the index a, it will help distinguish which one is chiral, which one is anti-chiral. So lambda minus would be defined with this kind of bracket, the square bracket instead of.
U plus is left-handed, right?
I'm sorry?
U plus is left-handed, right? So
Whatever, left, right, I don't know.
should it have negative values?
Again, plus or minus is not, I mean, left, right, it's a definition, it's not really.
Yeah, but
Yeah, I don't care what's left and right. You can, some people define something left, some people define the same thing, right? Left and right is just an index. Anyway, so the point is, I'll define this as so lambda plus as lambda a and lambda minus and lambda tilde a dot. Also, it's tilde here. And the so the bracket in this case is an angular one, and here is a square one. Okay. Or yet another notation, if we remember that this is a 4x4 spinner, a 4-dimensional spinner, I can write only the upper components in this case, or the lower components in this case. So lambda tilde dot. All right. So we did this for column spinners, that is, normal spinners. But on the other hand, we can do also for conjugate spinners, that is for row spinners, which would satisfy the bar condition, that is now u bar p slash equal to 0. And then, well, we get the bars of these things. So we get u bar plus is lambda tilde a dot, and u bar minus is lambda a. Oh, sorry, this is defined this way. Yeah. So, bracket to the left. And this one will be defined lambda tilde A dot, and this one as lambda, lambda A. Okay. So the indices in this case were up, and the indices in this case are down. Now, now the convention for this, for having up and down indices, has to be, raising and lowering the indices has to be done with a two-dimensional kind of metric, but with spinorial indices. And, well, there's only one such object, and that's the Levi-Civita tensor, epsilon. So the epsilon 1, 2, or 1 dot, 2 dot is defined as plus 1. And then, importantly, epsilon with indices down, since it's also lowered with the same epsilon, must be minus epsilon A B up. And then the same thing here. So I lower the index with epsilon, for instance, so I'll write this. And now, however, notice that it's important the order, because when I lower the index with a regular metric, which is so a metric is symmetric. So I can write x mu equal to g mu x mu, and I can write this also as x mu g mu, right? Because g mu is equal to g mu. But when I use an antisymmetric matrix, it's not the same. This is minus epsilon minus lambda b epsilon ba, right? So you have to be careful of the order. So the order is this one that I wrote. This is a convention, but the convention I use is this one. And then reversely, if I want to raise an index, I write this as epsilon a b lambda b. Okay. Again, being careful about the order. And then correspondingly lambda tilde a dot is epsilon a dot b dot, lambda tilde b dot, and lambda tilde a dot is epsilon a dot b dot, lambda tilde b dot. Okay. So these are two different sets of possible conventions, and you remember them by an arrow that points diagonally either upwards or downwards. The difference between the two conventions is a minus, right? So the one I have is pointing upwards. All right. So now an important thing to remember is that we're dealing with real momenta. Momenta p mu are real objects, but it will actually turn out to be useful to consider. So later we'll consider momenta that are complex. This is a familiar thing. I mean, we've seen that analytic properties in terms of, well, some kind of momenta are important for quantum field theory. I mean, sometimes we dealt with P0 and we looked in the complex plane for P0, but also for things like Lorentz invariance, so for S and T, it's also important to consider them as varying on the complex plane and then considering the analyticity properties in this S and T. And even further, this is something I'll not describe here, but just for your information, it's sometimes important to consider the generalization of the orbital angular momentum or the total angular momentum J from being not only real but integer to being just complex. This is also important. So for all of these objects, sometimes it's important to consider the complex version. And we will see next class that for the BCFW construction, it's important to consider complex moment. So we have to keep that in the back of our mind as one possibility that needs to be addressed at some point. But for the moment, we'll keep to real momenta. And so in the case of real momenta, we have that U bar plus minus is related to U plus minus. And also that lambda is related to lambda tilde, therefore. But in the complex case, this is not true. So it's something to remember for next time. So that in the complex case, U bar is not related to U, and lambda independent of lambda tilde. But in this real case, however, you know, we have the Dirac equation P slash U plus minus of P equal to 0. And then remember that the bar is equal to psi dagger I gamma 0, and this thing is off diagonal. So then taking the bar amounts to taking the complex conjugate transpose and also exchanging, this exchanges left and right. So that means that when I take the bar of this, I obtain this solution, but where I have the identification of lambda A equal to lambda tilde A complex conjugate. So I need to take the complex conjugate and then exchange left and right, which amounts to exchanging lambda with lambda tilde. Lambda and lambda tilde, remember, are in different subsets. All right. So for amplitudes, we'll be interested in the case where we have several momenta, and so correspondingly several helicity spinors. So we'll we'll put an index I on the momenta.
The transposition in the dagger doesn't the transposition in the dagger change the left and right?
No, the transposition just changes this with this, right? Transposition just changes.
We are not talking about matrix structure.
So we define this U plus of Ki in this case, where it has several momenta. We will denote it by I, by which I mean the lambda in IA. So this is just a notation that is useful in order to write amplitudes, where I just hide the fact that this is a lambda in the bracket, and correspondingly I just don't put I omit the index A. And then U minus of Ki, I write it as the bracket, square bracket I, and then this as lambda tilde A dot I. Okay. Now, it's important to remember that these objects, the lambda and lambda tilde objects, are independent, irreducible representations of the Lorentz group. They are the chiral and antichiral spinors. And so out of them, I should be able to obtain Lorentz invariance. So Lorentz invariance can be obtained from these representations without the need to, from lambda by itself and from lambda tilde by itself. But then, how do I contract this? Well, there's only one object, as I said, that has two indices, two spinorial indices, either of A or A dot type, and that's the Levi-Civitat tensor. So I denote by this double bracket really the thing that is standard, so the product of a bra times a ket state, where the product is obtained with the Levi-Civitat tensor, so epsilon AB, lambda IA, and then lambda JB. Okay, and in terms of this notation would be, well, U minus Ki, U plus Kj, remembering that this notation, the complex conjugate state changes the corresponding helicity. And then correspondingly we have the bracket, the square bracket Ij, understood again as the product of the square bracket states with the same contraction with epsilon, so epsilon A dot B dot, lambda I A dot, lambda tilde I A dot, lambda tilde J B dot, and that's u plus ki, u minus kj. Okay. So that means that in the case of real momenta, I can write the product ij as the square bracket ij complex conjugate, looking at this relation. So taking the complex conjugate of this one, I'll get into this one according to the relation that I wrote over here. But once again, I want you to remember that next lecture will consider complex momenta, in which case this will not be true. So for real momenta, that means that the product, the two Lorentz invariant objects are not independent. They are just complex conjugate of one another. And that's to be understood because really out of two momenta, I can write only one Lorentz invariant. All right. So, in fact, just to make connection with this, so if I have momenta pi mu, pj mu, that then are described in terms of lambda ia, lambda tilde ia dot, and lambda jb and lambda tilde jb dot, then I can write the Lorentz invariant that is of Mandelstam-like type, so generalized Mandelstam invariants. I can write this as, well, pi plus pj squared. And since I'm in the case of massless external states, so pi squared is 0, pj squared is 0, this is just 2pi dot pj. Okay, so you see out of the two momenta I can construct this Lorentz invariant. And you note that it doesn't matter, since the external states are 0, it doesn't matter whether I have plus or minus in here, because then it just gives plus or minus in front. So it's the same Lorentz invariant. Right? So that's why in this form we still have only one. What else? Yeah, so we define these helicity spinors, but from them we should be able to reproduce to reobtain the momenta. So we remember that trace sigma mu is 2, right? Sorry, 2 delta mu. So in the case is the same, trace of the sigma matrix squared is 1, and the trace is therefore 2. So I can write this then as trace p mu trace sigma mu. But then P mu sigma mu is equal to what we call P A B dot. And sigma mu would be with indices B dot times some other index, but this is taken a trace. So in the end we have the same index. So P A B dot, sigma mu B dot A. And since in this case we have the gamma mu's were equal to 0, sigma mu, sigma bar mu. This was with A B dot, B dot A, 0. You see, gamma mu with A B dot is equal to sigma mu, so this is the same as gamma mu, which indices, oh sorry. Yeah, it should have been sigma bar, no? Well, okay, the notation then is not very good. Well, I suppose I could put here bars. Nothing changes, I guess. Yeah. Yeah, perhaps I do this. I put bars in here to obtain sigma bar mu B dot A. In any case, this would be gamma mu with the indices B dot A. So, and then this thing is lambda A, lambda tilde B dot. And so you see that then this is the product of lambda, gamma mu, and lambda tilde. Right? So actually lambda tilde, gamma mu, lambda. So lambda tilde, gamma mu, lambda. Okay? All right, so then we see that we reproduce the momenta from lambda and lambda tilde with this gamma matrix in the middle. Okay. All right. 1, 2. Okay. So the matrix is sigma mu. There are 4 matrices 2 by 2. So they are a complete set in the set of 2 by 2 matrices for independence. So they're a complete set. That means that any matrix, if I write this as AB dot, any matrix MB dot can be decomposed into them, right? With some coefficients. But then by taking, by multiplying here with sigma nu and taking the trace, sigma nu B dot A, right? Taking the trace, then I get that. So this product, the trace of sigma nu is 2, 2 delta mu. So C mu is 1/2 then times, so obtain here that 2 sigma mu, 2 C mu is equal to MAB dot times this. So C mu is 1/2 MAB dot sigma mu B dot A. So I write that MAB dot is 1/2 M. Now we have to use a different number. MBB dot. No, whatever. MB dot. And here BA dot. Sigma mu. A dot B. Okay, so that means that we have the completeness relation sigma 1/2 sigma mu A dot B sigma mu AB dot is equal to delta AB delta A dot B dot. Okay. So we can use this completeness relation to rewrite the Mandelstam invariant Sij in terms of the Helsinki tuners. So let's write this. This was equal to Ki Kj, and now we use this decomposition. Yeah, maybe I should write this explicitly first. So this was lambda tilde B dot gamma mu sigma mu B dot A lambda A. Now there was a factor of 2, so 2 times a half times a half, it's 1/2 in the end. Lambda tilde B dot sigma mu B dot A lambda A. This was I. Then times the other one, and the tilde J, let's call this A dot, sigma mu, A dot B, lambda J, B. But now, with this relation, I have that this object is equal to this object is equal to delta AB delta A dot B dot. And so the point is it but there's something. So when I have, I should have said a few things. When I have lambda A, lambda I A, lambda J A, so contraction like this is equal to minus lambda I A, lambda J A. This is because of the contraction with the epsilon, because I said the convention, this convention minus this convention. However, here I have two such contractions, so I get two minus signs, so I could have written this like this. And now I get this delta, but, oh no. But here I had A dot B and not A B dot. I think that doesn't matter. It's the order. It's the order of indices in here. It seems it's transposed. Is not right here. Why don't I get it transposed? No. The only problem is sigma 2, right? Because sigma 2 is not symmetric. So if I take dagger of sigma mu, then I get the same. So the sigma mu are Hermitian, but they're not symmetric in general. So I just don't see the solution to this. Alright, let me continue, maybe I'll see the so now I will get lambda tilde I b dot and well, a dot, let's say, because of delta a dot b dot, times lambda tilde j a dot. And then lambda is this it? And that j down lambda. I think maybe this is it. In my notes I have lambda j a lambda I a, and I think this is actually the thing I'm supposed to get, which would mean I would need to have like this. Oh yeah, I actually needed this, right? No. So in this formula I would lower this index and then raise this index and transposed. No, but lowering the two indices gives two minus sign factors, so gives nothing. And I still left with a transposed. Anyway, I don't see the solution to this, unfortunately. I just know that the final relation is right, and I'm not sure why. But so this factor here, lambda I a dot lambda tilde I a dot lambda tilde j a dot up, is equal to this. So this thing was equal to lambda tilde j a dot up, right? So this is lambda tilde I a dot down, lambda tilde j a dot up. So this is ij, and this one is similarly. So this is lambda j a up. So lambda I a down, lambda j a up is ij bracket. But here I'm in the opposite order, ji. So this is ji. No, I actually even wrote it oppositely. It doesn't matter because All right, so we obtain that Sij is equal to Ij, Ji. Okay, but further we note from this definition we can see that Ij is antisymmetric. Because exchanging J with I is equivalent to exchanging A with B in the epsilon, which is antisymmetric. And the same thing for the other bracket. So that means this is also equal to Ij, Ji, if I switch both brackets. Now, for real momenta, we have seen that the angular bracket is equal to the complex conjugate of the square bracket. But then from this relation, and this is also equal, then I could write it as Ij times so minus Ij angular bracket, and then using this I could write also as minus let's say Ij times Ij complex conjugate, right? So from this I can deduce that the angular bracket can be written as square root of minus Sij, right? So that's a solution, but in here a phase would cancel out, so that means it's times a phase. And then from this one I'll get that the square bracket is minus Sij times the opposite phase with a minus sign because, well, yeah, because no, sorry.
Relation will be true.
No, sorry, there's a plus sign. What am I saying? Yeah, it's like this, and then, yeah, because I can also rewrite this as minus Ij complex conjugate. Yeah, I had a mistake in my notes. All right, so Ij square bracket is square root times a phase, and Ij angular bracket is square root times opposite phase. Okay. All right. So now we can continue with the kinematic identities between helicity spinors. I think I still need to keep this, so maybe I'll erase here. So the sum of a helicity spinors is obtained from the sum of helicities for spinors that we've seen before. We've written the formula that sum over US of P, U bar S of S prime of U bar S of P, so we think this is alpha and beta, would be equal to minus IP slash alpha beta plus N. Right, so this was, and in our case this is 0. And then we can also multiply by P left, that would be 1 plus gamma phi over 2, and P right, that's 1 minus gamma phi over 2. The point of this being to project onto a given helicity. So this projects onto helicity minus, and this one into helicity plus. So multiplying this from the left and this from the right, we can write that sum over the spin EL US of P U bar S of P right is equal to, so this is 0, and here I have P slash, but P slash was, sorry, P slash P left, P right. This one would have non-zero components only in the directions A, B dot, right? Because this one projects into the direction of chirality left, which means A, and this one projects into the direction of chirality right, which means B dot. So the only non-zero component of P slash A alpha beta is P slash A B dot. And then this one was defined to be lambda A, lambda tilde B dot. Right? So this is equal to minus I P slash P left, P slash P right, which is minus I P A B dot. Okay? So in a matrix form, I would write this as no, sorry, forget about this comment, that's irrelevant. But so the next statement would be using this formula, but now for sum over various momenta. So let's say I have momenta Ki mu, but that satisfy momentum conservation. That is sum over Ki is 0. And I put this sum in this sum of momenta I put in front of this relation. So I get minus I P left sum I Ki slash P right. This is 0 by the momentum conservation, but from this relation, this is minus I P A dot, which is minus I lambda A lambda tilde B dot. And so this is minus I now with our notation. This would have been the ket I, and this is the bra I. Okay, so now we have momenta here with an index I, and this lambda corresponds to the ket, and this with the angular ket, and this one to the square bra. So together we get that this is equal to 0. So we get the identity that sum over I is equal to 0. In the case of momentum conservation. Okay, so this is another useful identity when dealing with amplitudes for spinors that will have amplitudes with external helicity spinors. So we could rewrite these factors. Now, there's one more identity that is useful. That is known as the Skelton identity. There are various ways to write something that would be called a Skelton identity. Basically, Skelton identity is a manipulation of a simple and obvious statement that the totally antisymmetric product of n plus 1 objects, if only n are independent, is equal to 0. And the Skelton identity specifically applies to spinors in this case. So, so this is a trivially obvious statement, but in the end you end up with something useful. So in our case, we have lambda i's and lambda tilde i's, but these things are two components, and these things are other two components in a different direction. Right? So, and I refers here to 1 to n, corresponding to the momenta ki from 1 to n. But now, if these are two components, that means if I have 3 of them, and I totally antisymmetrized, now these 3 must be different, but there's no 3 different components because we only have 2 component spinors. So that means that this antisymmetric product must be equal to 0, and in particular I can make it into a single spinor doing a product of 2 of them. All right. So now writing this in terms of explicit factors, I would write what? So lambda I, then lambda j dot lambda k means, so yeah, lambda I would be this, lambda j dot lambda k would mean jk, and then total antisymmetry of 3 objects amounts to writing the the two cyclic terms, so k ij and j ki is equal to 0. Okay? And of course, exactly the same thing can happen if I put tildes in here. So instead of this equation with angular brackets, I can get one with square brackets as well. All right. Okay, so these are the useful relations between helicity spinors that will appear in amplitudes. So we have seen some properties relating SIJs with helicity spinors. We have shown how to obtain momenta from the helicity spinors, and we have found various relations between the helicity spinors. This, and the one coming from delta function here. So now it's time finally to start using these formulas. Now we've defined the kinematics, and let's do a calculation. Oh, sorry. Yes, one more thing. So before we consider an amplitude, let's also consider the helicity spinor formalism for spin 1. So until now, I've defined these helicity spinors for the Dirac equation, that is for spin 1/2. But as I mentioned already, the most useful case that will actually be treated next lecture is the case of spin 1. So we should extend these things to spin 1. So I only do for spin 1. In principle, spin 2 is also very interesting, but I will not consider that. It's somewhat similar to this. So actually in both cases, spin 1 and spin 2, we know that the helicity, that is the helicity for massless particles, that is the projection of spin onto the momentum, can take only two values. In the case of spin 1, we say we can have, you can think of helicity as the circular polarization of light, for instance. Circular polarization can be this way or this way, which according to the right rule means the spin being in the direction of the momentum or in the opposite direction of the momentum. Right? And for gravitons, it's a bit more complicated, but it's a similar story. It's a bit more complicated because the graviton the polarization corresponds to a quadrupole moment, which is not a vector, it's a tensor, but in the end, it amounts to the same idea. There's only two possible polarizations corresponding to a spin being in the direction of propagation or opposite to the direction of propagation. So h is plus minus 1 for spin 1, and h is plus minus 2 for spin 2, so in the massless case. So we'll consider, as I said, only spin 1. So we'll have again a set of momenta for the amplitudes. And then we want to associate also some helicities for these. Since we have the momenta, we have also helicity spinors. But we want to, but in this case we also must use a reference momentum Q corresponding to a lambda Q, lambda QA and lambda tilde QA dot. In the sense that QAA dot is lambda QA and lambda tilde QA dot. So in this case, so unlike the spin 1/2, in the spin 1/2 case, polarization referred to a specific spinor, so it was easier to relate to the helicity spinors to the lambda and lambda tilde. Now in this case, polarization refers to a vector, epsilon mu, right? A gauge field A mu should have some polarization epsilon mu of k, which can be either positive or negative, as I said. So now it's a little bit more complicated, but it's still kind of obvious what we should do. So we know that we have this object that acts as a vector, right? Between a lambda tilde and a lambda. Only thing is that in this case we need to choose a reference vector in order to obtain something non-trivial. Because if we use the same lambda and lambda tilde on the right and on the left and on the right of gamma mu, then we just obtain the momentum, and we don't want to obtain the momentum, we want to obtain the polarization, we want to obtain something different. So hence the need to introduce this reference momentum with reference lambda tilde. And so instead of being a polarization that depends just on momentum, now it's unfortunately also a polarization that depends on the reference momentum. Let's say this is for momentum Ki. And then we define this, but then, so this would have been the analog of P mu. But now we should define also, we should have to cancel in some sense the dependence on Q. So we have to divide by the product between lambda Q and lambda I. And well, with a normalization factor of square root of 2. And then correspondingly for the opposite one, defined with a minus sign and complex conjugate is this square root 2 Qi. Right, so these are the polarization vectors for the two cases. And I can be a bit more specific. I can so I can remember that well, sorry, Yeah, I can multiply in the same way as we did in this case, right? In this case, we multiplied with sigma with 1/2 trace sigma mu sigma bar mu. So multiply with, well, or rather with trace sigma mu sigma mu, and which is equal to 2 delta mu. And obtain then that epsilon mu, epsilon plus AB dot KIQ and this was also equal to sigma mu. So when I multiply on the right hand side with sigma mu, I get the same, I get a delta function, and no, sorry, I don't need to multiply by this. What am I saying? No, I just multiply by sigma mu AB dot, just like that. Then this is sigma mu, also AB dot, I mean BA dot, let's say. And then I get a delta function with a factor of 2. I get a 2 delta function from sigma mu AB dot, sigma mu BA dot. And so this one gives square root of 2 lambda q A lambda tilde I B dot over QI. Yeah. And then epsilon minus, similarly, AB dot AQ. The other one would be equal to minus square root of 2 lambda tilde AQ lambda I B dot over QI. Okay. So one thing to note, so if I remember that QI is, well, epsilon AB lambda Q A lambda IB, and QI square bracket is epsilon E dot B dot lambda Q A dot lambda IB dot. I can see that in epsilon plus I have lambda QA upstairs and lambda QA downstairs. So really in this one so it's independent of this reference momentum as it should be. Right? It's only dependent on the direction in some sense. And as far as lambda, as far as Ki, however, it is dependent because upstairs I have lambda tilde, whereas downstairs I have lambda. Right? So in epsilon plus, I have lambda q down, but lambda tilde I and lambda up and lambda I down. So this does depend on ki, but not on q. It's just a way that is really needed in order to define in terms of helicity spinors. It's not actual dependence. And the same thing for epsilon minus. Now, these are all massless spinors, so they satisfy the massless Dirac equation. So we have this equal to 0 and this equal to 0, but also q slash q plus equal to 0 and q slash q minus equal to 0. So then it means that I can multiply this. So this is this is equal to, let's say in this case, this would be KAB dot KI, I should have said. KIAB dot no, lambda. So this was with lambda A dot B, lambda B equal to 0, and this KIAB dot lambda tilde B dot equal to 0. So by multiplying with a corresponding momentum, so here I would multiply with say P with Ki CB dot, Ki CB dot epsilon plus AB dot would be proportional to Ki CB dot lambda tilde IB dot, but this is 0. So it follows then that and this multiplication amounts to a product of, so using the completeness relation that sigma mu AB dot sigma mu B dot A is delta A, sorry, BA dot is delta A B delta A dot B dot. It's 1/2. Using this, I can rewrite this product as just epsilon plus mu times Ki mu. So this is equal to epsilon plus KIQ dot Ki. But then, as I said, because of the Dirac equation acting on lambda tilde, this is equal to 0. And then similarly, and then of course also for the lower one. For the lower one, the only difference is I active this on lambda, but this still gives 0. So it's true also for the negative helicity. However, I can also use the product to act on the other index, to act on index A. So I can multiply, say, with Ki A dot A And now this will act on lambda QA, but this would give so Q A dot B lambda Q B equal to 0, and this one gives Q A B dot lambda tilde Q B dot equal to 0. So by multiplying with momentum on the other index, on the index corresponding to the reference momentum Q, I still get the same relation. So I get epsilon plus minus Ki and Q, also dot with Q is equal to 0. Okay, so these epsilons these polarizations are transverse to the momentum. That's how it's supposed to be. The polarization vector is always transverse to the momentum for gauge fields. But the new thing is also because of this construction, because I needed a reference momentum to be able to write polarization tensor in terms of spinors, then it turns out that the polarization vectors are also transverse to the reference momentum. So I have to choose the reference momentum such that it is transverse to the polarization vector as well. Okay, but that's fine. So other than this, there's no constraint at the moment, because as we saw, the epsilons, so epsilon mu was proportional, as we saw, with lambda q over lambda q in the plus case, and lambda tilde q over lambda tilde q in the minus case. So the dependence on the momentum itself cancels, and you're only left with this dependent on direction, which says epsilon has to be transverse to q. But also we have seen that that this is proportional to lambda tilde I, and then divided by lambda I, and this one was opposite, lambda I divided by lambda tilde I, right? The first one was lambda tilde I divided by lambda I in here. The second was lambda I divided by lambda tilde I. But these objects correspond to spin 1/2, to helicity 1/2, right? And this one corresponds to helicity -1/2. And correspondingly, this thing will have, since really the only thing that matters is the phase. Remember, lambda was square root minus s times the phase, and lambda tilde square root minus s times the opposite phase. Not lambda, but the product of lambdas. This one, the ratio of lambda tilde over lambda will have helicity +1, +1/2, minus -1/2. Since the denominator has -1/2, but 1 over it will have opposite helicity. And then this one has the opposite. It's -1/2 minus +1/2. So this one has helicity -1. So that's why we were able to write this. Okay. So we were able to write polarization vectors in the massless case in terms of the same helicity spinors, plus in this case of a reference helicity spinor. So now let's calculate something finally. So let's say amplitude with helicity spinors. So we could, in the next class, we'll be mostly interested in the gauge theory case. But in here, we'll just make use of the formulas for helicity spinors and rewrite something we already calculated in terms of helicity spinors. So we've considered this this Feynman diagram, which we saw was given by this Feynman diagram. Let's say L bar. Okay, and we'll consider it in the massless limit. Right? Yeah. So yeah, I should have said E bar. The point is instead of minus and plus, I'll use unbar and bar because minus and plus is reserved for helicity now. So we've calculated the result for chirality, or given chirality, but then in this case this was the same for helicity. In the massless case, we saw that this is the same as helicity. And so in particular we had, for instance, this one. E plus left of minus K2 going to L left of K3, L bar right K4. So we've calculated this one, which now we can say it's like this. And this minus K1 minus K2 is simply that I want to use the convention that all momenta point in the same direction. And so if I define this to be helicity plus, this helicity minus, then this is helicity. This one is helicity plus. This is helicity minus. Since they're in the opposite, so complex conjugate with respect to the final ones. The amplitude then is written as A4 in the 3 case. Now, the notation, remember, I use a notation where I index the momenta by the index I. So I have momenta 1, 2, 3, 4. Then I will put the states as corresponding to this index, plus the index of helicity. So 1 plus E bar, 2 minus E, then 3 plus lepton, 4 minus antilepton. Okay, so this is the amplitude that we had before. And now we just substitute the formula. So the formula we had found before was A4 is equal to I squared over K1 plus K2 squared V minus bar of K2 gamma mu U minus of K1 U plus bar of K3 gamma mu V plus of K4. With our notation, we call this S12. So I E squared of S12. Then this one, so the only non-zero thing in here would be sigma mu A dot. Then this object would be lambda 2, so for the index 2 of with index A. And here we get lambda 1 tilde A dot. And here again, this would be non-zero only for B dot B. And then this corresponds to lambda with index 4 for the momentum 4 B. And this one corresponds to lambda tilde 3 on the index 3 B dot B dot B. Okay. All right, and so let me write this again. I squared over S12 lambda 2A sigma mu A dot lambda tilde 1 A dot and lambda tilde 3 B dot sigma mu B dot B lambda 4 B. But then there's a factor of 2 different. So the point is, now I can use the completeness relation. Sigma mu A dot sigma mu B dot B is, well, I thought it was 1/2, but anyway, delta AB delta A dot B dot. And then I have lambda 2A with lambda 4B. So it's E squared over S12. Lambda 2A with lambda 4B. That means 2, 4. And then lambda 1A dot with lambda 3A dot. So that's 1, 3. Okay, so this A4 which was equal to A4 for 1 bar plus 2 E minus 3 plus 4 L bar minus is equal to this result. And then further, I remember that S12 could be written as 1 to angular bracket times square bracket 2, 1. So this is then IE squared 2, 4, 1, 3 over 1, 2, 2, 1. All right. So this is an example of what we want to obtain. So this is a very peculiar example in the sense that there's only one Feynman amplitude, only one Feynman diagram. So the Feynman diagram is equal to the actual three amplitude. And then the amplitude at 3 level, then it's written in terms of, only in terms of these products of helicity spinors. And this will turn out to be the case in more complicated amplitudes as well, where we don't have just a single Feynman diagram, because that's not what's interesting, but we have a huge sum of Feynman diagrams, and yet still the final amplitude will be written like something of this type, like a ratio of products of helicity spinors of this type. Yeah. All right, so that's everything I wanted to tell you. Let's see. All right. So that's everything I want to tell you today. Do you have any questions about this? Wow. Okay. So since I will not. I will not consider this helicity spinor formulas for the exam. I'll just give you an. You just need to give the homework for this class next time, but not for the next class. So next class is on Monday, and Monday. Then the class is just for your own interest. You don't need to do homework. You don't need to study it for the exam either. So it would be useful there, but it would be useful if you would have some questions. If you would think about some questions from the course, because that will be the last time you'll have to ask me questions. So, I don't know, do you have some other questions that you want to ask about other lectures? Well, okay. As I said, if you can think about some questions next time is the only possibility, so let's finish here.